My dear friends, welcome to Rajashekar classes on applied data science with Python. This is lecture number 360. In this lecture, we will try to understand maxima and minima. Since we have gone through some basics of calculus or basics of differentiation, let's understand what is maxima and what is minima. Imagine if I have function like this, just this is my function. In this function, what is this? This is my x, this is my f of x. If you observe carefully, just try to understand maxima and minima of this particular function. What is this point? What it indicate? This is the maximum value. This is the maximum value that function takes, isn't it? In similar manner, what about this point? This is the minimum value. That is the minimum value that function takes. One thing that you will notice here, both at minima and maxima, if you look at the slope, let's look at the slope at minima as well as maxima. What is your slope? At minima and maxima, the slope becomes 0. What is slope? We already discussed what is slope in our previous lectures. Next important thing is there will be some functions which do not have maxima. What is this? Do not have maxima. Do not have maxima, isn't it? There will be some function which do not have maxima. For example, take this function y equal to x square. This has minima. This particular function has minima at origin. But there is no maximum. Because as x increases, let's say as x increases, your y is also increasing, isn't it? Y is increasing continuously. There is no end. There is no max, isn't it? As x increases, y is continuously increases. It never stops. Similarly, as x decreases, just say x decreases in negative side, it is continuously to increase. Just say it is continuously to increase. So this function has no maxima, it has only minima. There is no maxima. It never stops, isn't it? It has only minima. It has minima at x equal to 0. Similarly, let's take some other function. Let me consider function like this. What about this function? Just observe this function. What it says? This function has, I can say, this function has maximum at x equal to 0. It has no minimum. It has no minimum, isn't it? Because it keeps going. So it's possible that you may or may not have maxima and minima, isn't it? Just let me consider one case where the function may not have maxima and minima. Just observe this case carefully. I have this function. Now this function has no minima and no maxima, because this keeps on decreasing, isn't it? This keeps going on to what? This keeps on going into, what is this? Minus infinity. This keeps on going into, because this keeps on going into plus infinity. There is no end. Even this case, there is no minima, there is no maxima, isn't it? There is other case. Just let me explain one more simple case. Just see this one. What it says. Just observe this one carefully. Let me say, suppose this is my function. This is my x, and this is my f of x. This function has two minima. isn't it? What is that? Let me show like this. Yes, this function has two minima, that is m1 and m2, isn't it? This function has two minima. If you notice, this is the minima. Just see, this is the minima. Why it is the minima? This is the minima because slope here it is 0. Just find slope. Slope is here is 0. There is other minima. This is also minima, isn't it? Because slope here also slope equals 0. If you look at corresponding points in the vicinity, all the points have greater than, just if you observe here, corresponding points in the vicinity, all the points in the vicinity have greater than this value. This is minimum 1. Let me say this value is minimum 1, isn't it? And this is, let me say, this is minimum 2. So you have two minimums. This is minimum 1, this is minimum 2, isn't it? It's two minimum. So it's possible that a function has multiple minima, multiple maxima. So this, what we have to do here, there are two maxima. Just see here, this is maxima 1 here, I have maxima 2, isn't it? Because with respect to this locality, with respect to this local points, this particular point is maximum point. Because with respect to locality and with respect to the neighborhoods of this particular point, if you look at the neighborhoods, in this neighborhood, this is the maximum point. Here in the neighborhood, this is the minimum point. In the neighborhood, this is the minimum point. This is also, this is in the neighborhood, this is minimum point. In this neighborhood, this is the minimum point, isn't it? Now, what does it mean? Because amongst all minima, which one is lowest? Let me say, this is minima, this is minima. But in all these minima, which one is lowest? This one is lowest. So it's possible that a function have multiple local minima, but it always has one global minimum. Minimum of all the minima. What is global minima? Global minima is minimum of all the minima. All the minima. Isn't it? How many minimums here you have? One minima and another minima. Which one is the minimum among the in these two minimums? This one is minimum. Therefore, this lowest value, I can say this is global minimum. Maximum of all maxima. This is maximum 1. This is maximum 2. In this locality, this is maximum. In the neighborhood, this. But which one is maximum among these two? This is maximum. Therefore, this is known as global maximum, isn't it? What does it? Maximum of all the maxima. Maximum of all the maxima is global maxima. Global maxima, isn't it? For example, here, what is this? Here, this point A is, this is local maxima. Local maxima. This, let me say, this is global maxima. Here you have two maxima in which this one is bigger, isn't it? So it's possible to have multiple minima and minima. Anything that is not a global minima is called local minima because in its neighborhood it is the smallest value, isn't it? In the neighborhood, it is in the neighborhood here. In the neighborhood, it's the largest value, and then it is called local maxima, isn't it? This point is local maxima. So we have seen a simple example here to find minima. Now let's take slightly complicated example. Just let me show this one. Let me summarize. Yes, what it says. Same thing here. This is global maxima. This is local maxima. This is local minima. This is global minima. A function has multiple minima and multiple maxima. Now we will try to understand one simple example. Let me take a simple. Now let's take a slightly complicated example, slightly more complicated. Imagine my f of x is equal to, let me say, log of 1 plus exp of ax. exp of ax. Otherwise, let me write in another slide. Yes, let me consider my function f of x is equal to log of 1 plus exp of ax. This looks something like logistic loss, isn't it? It's look like logistic loss. In logistic loss, instead of ax, we have yi into w transpose x. Anyway, let's assume a is constant. What is a? A is constant. A is constant here. Now, if I want to find minima and maxima of this function, so necessary case we found very easily by just saying df by dx equal to 0. This is the necessary case, isn't it? And just solve df by dx equal to 0. How can I solve this df by dx? By solving the, for example, if it is simple equation, I can solve. For example, there is something like x square, and if there is some function, let me take one simple example here. For example, I will consider this function. Let me take x square minus 3x plus 2. If this is my f of x, I can easily find f dash of x. How can I find? X square differentiation 2x, 3x differentiation 3, 2 is constant 0. My f dash of x is 2x minus 3. I can solve. F dash of x equal 0 means 2x minus 3 equal 0. I will get x equal to 3 by 2. It's simple thing. But what happens for log of 1 plus e power ax? If I differentiate it, what will I get? 1 by, log means what? 1 by exp of ax. Isn't it? Again, chain rule I must apply. If exp of ax means what? I will get exp of ax, and ax differentiation is again a. Isn't it? A into exp of x. This I must equate to 0. Previous case, solving 2x minus 3 is easy. Isn't it? You can easily solve, trivial. But in this case, solving a into exp of ax by 1 plus exp of x is not trivial. Sometimes it's very, very hard. In some cases, it is very, very hard to solve this f dash of x equal 0. So, if you want to find minima and maxima, just trying to solve df by dx equal 0 may not always best way, especially complex functions like log of 1 plus exp of ax. So, we will see some techniques, some computational techniques to find minima and maxima in my next lecture. Technique is called gradient descent, which is a computer algorithm to find maxima and minima without having to solve this equation df by dx equal to 0. This is very, very important because sometimes it is very hard to solve df by dx equal 0. In such cases, we will use an iterative algorithm. Remember, calculus is almost 350 years old. Modern computer science is 100 years old. Modern computers which can do good calculation is almost less than 30 to 40 years old. Maxima and minima has got so many applications, just not in machine learning, in physics, in business. There are tools, there are tons of application for finding maxima and minima. Data science is just a small area where we use maxima and minima. Just go through this. I will discuss in detailed manner about this maxima and minima in future lectures. In future classes, we will discuss about grad, vector differentiation grad. Thank you very much.